Hi everyone, it's me, Carolyn, and in this video we're going to be looking at the hypotheses test that we can use for the difference between two proportions. Although we sometimes don't set them up as the difference between two proportions, I will make that connection for you, just so that you can see why it is called that. There are tests for the difference between two means as well. However, I will not be having videos at this time for those due to time restraints and the fact that I don't cover those in the course that I am currently teaching. So I will not get to them at this time. I do use SALT for these problems, mostly to save me some time. There are other statistical softwares out there that can do a lot of the work as well. I just happen to have my students be using SALT, which is a Cengage product. So I'm going to just jump right into an example because by this time we have seen the process of doing hypotheses tests. So the process is pretty much the same for every single one that you do. We go through the same 5 steps. However, there's little differences in each step, like exactly what those hypotheses are going to be, exactly what checks we look at, exactly what is the formula for our test statistic. Although nowadays we don't necessarily need to actually calculate that because the software will do it for us. Same with calculating our p-value. Also, this is a method using the p-values. I tend to lean that way in today's world, mostly because of all the technology that we do have available to us. So I'm going to just jump right into an example. So here we have an example that says that many students who start primary school aren't ready for the classroom. In the Northwest, 39% of school leaders surveyed said that more than half were not ready for school. In the Southwest, 26, and that should have been a percent symbol, had the same view. Assume that a random sample of 200 from the Northwest and 300 from the Southwest were taken. Is there enough evidence to show that the proportion of leaders in the Northwest is higher than that in the Southwest? And we're going to use alpha equal to 0.05. We will need a little bit more information further down the road. Yeah, because I didn't. Oh, never mind. We're just going to try to find out if there is Northwest is higher than the Southwest. Spacing here a little bit. So we will start with our 5 steps, and I did leave spaces for all of those pieces. So step 1, first of all, as it is with all of them, is to write our null hypothesis and our alternative hypothesis. And again, I want to remind you that if you pick up a different textbook, the alternative might use a capital A, it might use the number 1. But here we are looking at 2 proportions. We're looking at the Northwest and the Southwest. So in other words, we're going to start with our proportions being equal to each other. Most textbooks will start with a P1 equal to P2. However, I like to use subscripts that make sense to me in the problem. So I might use an N and an S instead. So the proportion in the Northwest is equal to the proportion in the Southwest. And then I can write my alternative because we are saying the Northwest is higher. So that helps me determine which way that inequality is going to go. If I do them generically, it's harder for me to keep track of what numbers are going to go where when I get to my software. Now, we do call this the difference of 2 proportions because what we usually do, I'm going to take these 2 pieces and I'm going to basically take this variable and put it on the other side. So to do that, I'm going to have to subtract it. So this is where that idea of difference in proportions comes from. So we're looking at the difference in these two being equal to 0 versus the difference being greater than 0. However, I still like to write my hypotheses in this form because it makes more sense as far as the problem goes. You can translate them into this as the software will if you want to. But again, there is no definite need to. Okay, this is going to be a two proportion z-test if the following conditions are all met. First of all, that we are looking at two parameters and we kind of are looking at the difference in them. So again, can we write it in this form? Yes, we can. Do we necessarily need a 0 there? No, we do not. However, in all introductory courses, most of the time it is a 0 there. But we could say something like the proportion in the Northwest is more than 5% more than the Southwest. You could state things of that nature. So it does not necessarily have to be a 0. The samples that we take are going to be independent from each other. So we want to make sure that they don't have any relationships between them. I'm going to assume that the Northwest and the Southwest are completely different. Okay. The other thing that I need to make sure happens is that all of those little pieces, like we did before, are bigger than 10. So if we take N1 times P1 and N1 times 1 minus P1, N2 times P2, all of these things have to be bigger than 10. So we want to make sure that every place or every sample has more than 10 successes and 10 failures. If that's not the case, then we might not be able to do, well, we can always do the tests, but the results may not be valid. Okay, so we're going to check that in this case. So just kind of writing all my pieces. If N, and I'm going to put capital N, and I'm also going to do Southwest here on this side here, so NS. So my Northwest had a sample of 200. And my Southwest had a sample of 300. In my Northwest, that proportion was 39%, so 0.39. In the Southwest, we had 0.26. So now I'm going to look at N times P, so that 200 times my 0.39. And I multiply those, I get 78. I'm going to do my 300 times my 0.26, which is also 78. That's really weird. That is just a coincidence. I take 200 times 1 minus 0.39. That's going to be 200 times 0.61, which is going to give me 122. I'm going to do that for my Southwest as well. 300 times 0.74, which is 222. Okay, so those are a little different. But notice that these are all larger than 10. So we can go on and use our normal curve, or we can do that two sample proportion test, which is what we will be using in our SALT. Okay. So now our test statistic, if we were actually going to calculate it by hand, which I am not, but I will find all of the pieces. We would take our P1, our P hat 1 minus our P hat 2, and we're going to take that and divide it by the square root of this P hat C, 1 minus P hat C, and so forth. Now, P hat 1 is the sample proportion for sample 1. So for our place, that's going to be our Northwest. That was our 0.3 something, 39. Our P hat S, which is our second set, that is our 0.26. N1 is our 200, N2 is our 300. So right now I would be putting in 0.39 minus 0.26 all over. This would be a 200 and a 300. Okay. P hat C, which is what shows up in the square roots. Notice the square root does go over the entire thing. This formula is a lot more complicated to calculate by hand. So thank goodness we do have software to do this. That P hat, we use a little C in our textbook. That stands for a combined proportion. Other textbooks may refer to this as a pooled proportion because we're kind of combining the two together. What we have is the total number of successes for number one, the total number of successes for number two, all over the total numbers added together. Luckily for us, we've already calculated these two values when we did our checks. So we did do N1 times P1, that was 78. N2 times P2 is also 78. And then we're going to take our two N's and add them together. So out of our that's a 300. Out of our total 500 people that we asked, we have 156 that thought the students were not ready to go. So I'm going to just double check my adding here. And then I'm going to turn that into a decimal for us. So I get 0.312. And that's the number that's going to go in here for those pieces, 0.312, and then 1 minus 0.312. And then we'd have to crank that number out. However, I am going to let SALT do the work for us from SALT. But that's would be our values. Step 4 is going to be to calculate our p-value. And again, I will let that come from SALT. I also make note of my alpha level. My alpha level for this problem was 0.5. 0.05. And then we'll draw conclusions and interpret our meeting. So I am going to go to SALT to do all of the work for me. So let's go into SALT. And I know I'm not on the right screen because right now I'm looking at a one sample proportion. We did not have one sample. We had two. We had one from the Northwest and one from the Southwest. So I'm going to have to change what test we're doing. And we are doing a two sample proportions because we're looking at the proportion of our Northwest, comparing it to the proportion of our Southwest. Now, here's where we have to make sure to keep things a little bit organized. So the number of successes, this would be the thing you set first. So in our case, it was that Northwest. So that's going to be my 78, which we calculated out of the 200. This is that 78 out of the 300. And you would calculate these number of successes if they weren't stated. You'd actually calculate them when you do your checks. So that's that N times P that we had. The hypothesized test difference, that's going to be the 0 that we saw when I put them on one side. So when I wrote them as Pn minus Ps, then it was equal to 0. This is that 0. And we were doing it versus, I wanted to say we did a greater than. So I have to change this to a greater than. And I'm going to generate my results. Okay, so here's my hypothesized values. Now they do it in general, P1 minus P2. So mine were Pn minus Ps equal to 0, Pn minus Ps greater than 0. So a reason for writing them on one side would be to check to see if it's set up the way you want it to be. The difference in those two proportions is 0.13. So they took the 26 and that 39% and subtracted it. The common, there's that 0.312 that we had done. That's that P, that common or that combined or that pooled proportion that we calculated at the end. My standard error, that's the square root thing on the bottom. There is my test statistic, so 3.073707, and then my p-value, which is 0.001057. Okay, and you can kind of double check down here on the bottom too, making sure that you have your first one put in the correct order. So my Northwest was my 200. There's that 0.39 that we were given. So it also double checks my 78 for me. My 0.26 that we were given. There's my 78 that we had to calculate, and my 200 and the 300 that were given. Okay, so now I can go back to my main screen to actually make my decision and to write my conclusion. So here was that test statistic, which is 3 standard deviations above the mean. So thinking 68, 95, 99.7, we got some little tails up there. Here was that pooled, which we saw in our SALT screen at 0.312. We didn't actually have to calculate it. It did it for us. And there's my p-value. So in step 5, we compare our p-value to our alpha level, 0.001057, the alpha level, 0.05. Is this smaller than that? Yes, it is. So we reject. Okay, nothing changes as far as what we compare. We still compare our p-value to our alpha value. Alpha is setting up our comfort level, our boundaries. The p-value is what's associated with our statistics, with our sample. So that's not something we have a lot of control over. That is completely determined by the sample we had. This one is setting up somewhat of confidence for us, how important this decision may be. But in this case, we are going to reject, which means there is enough evidence or significant evidence to show that the proportion of school leaders in the Northwest is greater than the proportion in the Southwest who feel that more than half are not ready for preschool, not ready for school. More than half of primary kids are not ready for school. Okay. And that would be something I could publish. I would have my statistical analysis to back that statement. And that's what the statisticians do, is they do all of that work for this one little statement. They may explain in their publication as to how they got their samples, how many people they had, what those samples looked like, and so forth. But it's all the work to go into that one sample. Okay, let's do another example. I think I have one more after this if I feel it is necessary. By this point, though, I think we are getting pretty good at things. So I'm just going to do this one last example. So we have in recent years, there has been concern over lead contamination of drinking water. In Virginia, 19% of the 2144 wells sampled had lead concentrations higher than the EPA recommended as safe level. And in Pennsylvania, 24% of the wells sampled were higher than the EPA. Does this data, or do these data, provide evidence that Virginia has a lower proportion of poor wells than Pennsylvania? Okay, so going through our 5 steps and using SALT to help us do the analysis. So we've got our 2 hypotheses. So we have to, again, when we're writing hypotheses, determine what type of situation do we have. So we have to be able to read this question and realize that we are talking about 2 different proportions. We have a proportion for Virginia and we have a proportion for Pennsylvania. So I'm going to start with the proportion for Virginia equal to the proportion for Pennsylvania. And that is going to be compared to our proportion of Virginia being lower, so smaller than the proportion of Pennsylvania. Step 2 is to do all of our checks. So we have to make sure that our n's times our p's and our n times our p hats, p1s and p2s. So I'm going to do our Virginia, and I'm going to have to do our Pennsylvania. Pennsylvania. So number for Virginia, 1 minus. And we'll also have to do the one for Pennsylvania as well. Well, in Virginia, we had 2144 wells, and 19% of them were poor. So I'm going to drag out my calculator, calculate that value. So that's not one I can do in my head. And we get 407.36. I'm just going to say 407 because they rounded. Obviously, we cannot have partial wells. Here I'd have that 2144 times our 1 minus 0.19, which is 2144 times 0.81. And that gives me, and again, I'm going to round to the nearest whole, 1737. So notice both of those are larger than 10. Here we had in Pennsylvania, we had 251 wells, and 24% of them were poor. 251 times 24%. So that is going to be 60. So here we're going to have that 251, 1 minus 0.24, which is going to be 0.76. And I get 191. You should be able to check a little bit. And adding these guys together, you should get your total. So if I took my 60 plus my 191, I should get my 251 wells. This is the number of successes. So there are 60 wells that weren't good. Here there's 407 wells that weren't good. And this is why you would not compare the numbers. Because if you look at the numbers alone, we have quite a few more wells here that were poor than there. But our proportions, so we want to make sure to compare proportions and not numbers. So we can kind of compare the exact same things. But again, all are larger than 10. So we can use that normal curve that is embedded into that software for the 2 proportions. So again, now we're going to go to step 3, which again, we're going to get from SALT. So we will get that test value, which is going to be a Z value. And I could, while I'm there, is kind of get that pooled if I wanted to, that pooled hat, which I could have gotten by taking that 407 plus the 60 out of my total 2144 plus the 251. Not that I need this number, but that's my pooled proportion. Maybe I want to do more analysis on some other front, and I might want that number. Who knows? This is step 3. Step 4 is that alpha level, which in the problem is 0.01, and our p-value, which we'll get from salt. This is also going to be from salt. Then we'll come back, do step 5, which is to make a decision and to write a conclusion, basically answer the question that is being asked by this problem. So we're going to let salt do all the work for us, though. All the grunt work. Software is wonderful these days. So a 2-sample proportion. So this is going to be my Virginia. So Virginia had 407 out of the 2144. Pennsylvania had 60 out of the 251 wells. The hypothesized difference is 0 because I just want to know, are they one bigger than the other? Not bigger by 17% or whatever. And we are doing a less than, I should say smaller, less than this time, and generate my results. So Virginia minus Pennsylvania is equal to 0. Virginia minus Pennsylvania less than 0. There they actually subtracted the two. It's going to be a little different than what we were given because notice, I'm going to go down here a little bit further. This is my 19%, 0.1898. We had rounded it a little bit because we know that our number of successes cannot be a decimal value. We can only have 6 wells, not 6.3 wells. And here's that 24% that we saw. So they had rounded those when they stated them in the research or wherever. So we have these values. And a lot of times I would think that they would actually just tell us the 407 out of the 2144 and the 60 out of the 251. But here's all of our pieces. Our test statistic is down here. There's that common P. I'm going to write it down so we have it. My test statistic is a negative value because we wanted to show that Virginia was smaller. So if I take Virginia minus something bigger, it should have been negative. And my p-value is 0.031308. Okay. We will go back to our screen, to our main screen, and finish this problem off. Okay, so here was our combined. There was our test statistic. We were down below by negative 1.8. There's my p-value. There is my alpha value. We want to know if this value is smaller than that. So our p-value is 0.03, alpha is 0.01. This is not smaller. So we will not reject, do not reject. Okay. So this is probably Pennsylvania doing the test, choosing a 0.01 because they didn't want Virginia to have bragging rights. If I were Virginia, I would have maybe done a 0.05, then I could have rejected. And then I could say that our wells are better than Pennsylvania's, but we have shown that there is not enough evidence. And some people might even put in at alpha equal to 0.01 or at the 1% level, something like that. Some people put that in there, some people do not, because a lot of people, general public does not understand this whatsoever. Anyone in research probably would, but there's not enough evidence to show that the proportion of pore wells in Virginia is less than Pennsylvania. Okay. Whereas if I were someone in Virginia, I might have changed that alpha level to then we would have rejected. And then I could say that Virginia has less pore wells than Pennsylvania, trying to pull people from Pennsylvania to come to Virginia. So there is a lot of sometimes manipulation that can happen with the alpha level and things like that. So it really depends on who's doing the research, who's doing the surveys, who's doing all sorts of things. So when you're reading results, please take the time to ask yourself who is performing these things. What do they want me to show? Why did they choose an alpha 0.01? Why not 0.05? 0.05 tends to be the most common. And I think it all comes down to that 95% idea, which is 2 standard deviations away in each direction. If we were doing a two-tail, that would be that 95%. Yeah, so just kind of start asking yourself those questions when you're doing your reading of research. Make sure you start thinking a little bit more critically about what you are reading or hearing. That concludes this lecture video, and I hope to see you in other videos. If not, have a great day.